Hello, everyone. So today we are going to be starting a new conversation on a new topic in physical chemistry. So today we're going to be starting to talk about symmetry. So symmetry is one of those topics we've been bringing up a little bit here and there as we've been going through atomic and molecular orbitals. So one of the things that I want to go ahead and first start with is why I should care about symmetry. So when I'm talking about symmetry, one of the biggest things that it has is it's a way to really help narrow down the possibilities when we're talking about things like combination of orbitals, excitations in between various electronic states, distributions of electrons. We're constantly running through this problem of there just being too many possibilities, too many possible combinations of atomic orbitals, too many states that we can excite electrons from and to. So symmetry is going to be our major method of simplifying the system. And it's worth noting that this is one of those ideas that we've been bringing up a fair bit already. One of the classic examples was when we were first bringing up the idea of molecular orbitals and how I can combine s and p orbitals to make bonds. And we said that we could combine s and pz orbitals because they had the same symmetry, that they'd have completely constructive overlap. But we said that S and PX had different symmetries, and so they would have essentially canceling out constructive and deconstructive overlaps. So what we did was we made a symmetry argument that we couldn't combine certain types of atomic orbitals to make molecular orbitals. So this is the reasons why we really find symmetry being important. It's going to simplify a lot of the topics we've been talking about already. But here's the issue. We first need to really define symmetry. So when I say use the phrase symmetry, what we're describing is that an object is symmetric if there's some sort of action or movement I can perform on the object that still gives me my original object back. So I take some action, which we are going to call a symmetry operation. So I'm going to take this action about some symmetry element, and when I do that, the object looks exactly the same as when I started. So some of these symmetry operations will seem familiar, and some will probably be new. So there's three major symmetry operations that we're going to use to construct a lot of our symmetric systems. So we've got a rotation, at which point I rotate my object about some line or axis. A much more common reflection, where I have a reflection across a plane to get the same image back, or the one that we've used previously, the inversion symmetry, where I can invert the entire structure through a central point and the image looks exactly the same. So this is a lot of kind of arcane terminology. So let's look at each of these symmetry operations individually to see kind of what they look like. So the first and probably the most important symmetry operation that we're really going to be talking about is called the n-fold rotation. So this might seem a little bit familiar, but the idea of an n-fold rotation is this going to refer to how many times I'll get a symmetric image, an identical image, if I rotate an object a complete circle or 360 degrees about some central axis. And this is going to include the final slash initial structure. So let's actually play through this with an example case. Let's go ahead and look at how many times I can rotate benzene about some axis and still get the same image back. So what's the highest n-fold rotation for benzene? So if I've got my benzene molecule, one of the rotations I can have is I can flip it about. So take this hydrogen, move it over here. And if I do that, that would give me a C2 axis, as I would flip it once, flip it twice, get it back to where I started. So I'd have one image, two images. Alternatively, and probably the one that really stands out for benzene, is I can go ahead and take this hydrogen, rotate it 60 degrees, and end up with an identical structure, except for all my hydrogens moved one place. And then I can do this 5 more times, moving it sequentially around the ring. And then a 6th final rotation gets me exactly where I started. So when we do this, what we're really demonstrating is that benzene has a C6 or six-fold rotation about this central axis. So I can rotate it 6 times and get back to where I started. So this is what I'm really talking about when I'm talking about an n-fold rotation. But again, one of the things to watch out for is there might be some rotations that are harder to see than others. So for example, I have C2 axes about axes, C2 rotations about axes that run through this hydrogen carbon hydrogen line. So we're going to have multiple C2 rotations running through each of these bonds, as well as several more bisecting. So this is a classic set of n-fold rotations. But one of the most iconic of our symmetry operations is going to be the reflection. So when we're talking about symmetry, especially in organic chemistry, we're always talking about a mirror plane. And this is a type of reflection. So when I say that I have a reflection, it indicates that an object has a mirror plane running through the object. So there's some plane that I can cut through the object, and I'll have an identical image on either side. Now, here's one of the real problems with mirror planes, is I need some way of indicating which mirror plane I'm talking about, because something like benzene is highly symmetric, and it has multiple mirror planes. So we've used 3 typical definitions of a mirror plane. The first one is going to be the horizontal plane. So this is given with respect to our principal axis of rotation, so our highest n-fold rotation, in this case C6, and the horizontal mirror plane is the one that essentially cuts perpendicular or straight through or across the C6 rotation. So this is the one that's in the plane of the molecule, because since I have a planar molecule, everything above and below the plane should be exactly identical. So it's always good to make note of these horizontal planes of rotation, as they're ones we don't normally think about. Instead, we're often much more thinking about what's called a vertical plane. So this is one that cuts parallel, or I like to think through the principal axis. So my principal axis is a line that cuts through right here. So my principal axis cuts in a line straight down the middle. And so my vertical plane essentially includes that principal axis. So it's one line in the entire plane. And so any mirror plane that cuts through that principal axis is called a vertical plane. However, since there are a fair number of vertical planes, we do have a special subcategory for something called a diagonal plane. So this is a vertical plane that bisects in between 2 C2 axes. So I have a C2 axis that cuts through this hydrogen-hydrogen coordinate, and one that cuts through this hydrogen-hydrogen coordinate. So I have a diagonal sigma v, or vertical plane, that bisects the two. So this is a classic case of all thumbs are fingers, but not all fingers are thumbs. Sigma d's, or diagonal planes, are a special subcategory of a vertical plane. So this brings us to our third symmetry element, and this is one that we've seen before. It's an old familiar friend, inversion symmetry. So we already used this guy to help classify our atomic or our molecular orbitals, as we had our bonding atomic orbitals had a center of inversion. So I have an inversion center if for a molecule, if I can project every point of the molecule through the center of inversion and end up with an identical point. So again, this is a case where, again, benzene satisfies the rule. We will have a center of inversion straight through here, and I can map every single one of my carbons onto a carbon on the opposite side. Same thing with my bonds, and same thing with my hydrogen atoms. Something is considered to not obey symmetry if there's something that's even slightly different on the opposite side. So for example, our Girard symmetry contains a center of inversion. Our Ungerad does not. So this is hopefully familiar. We've played around with this one before. However, we have two last slightly oddball symmetry operations. The first of which is called an improper rotation. So this is a combined symmetry operation where I first perform an n-fold rotation, which will generate a principal axis, and then I'll reflect the object across a horizontal plane that bisects that axis. So now this is, let's be honest, just a really confusing mess of word soup. So let's work through a quick example. I have methane. So methane possesses an S4 improper rotation. So what an S4 improper rotation is I rotate my whole molecule 90 degrees, and as you may note, I do not have a C4 axis for methane. 90-degree rotation does not get me back to where I started. But after I do that 90-degree rotation, I can reflect across the perpendicular plane, and I end up generating a hydrogen exactly at that point. And this will happen for all 4 of the hydrogens, and the carbon doesn't move. So this is one of the very cool things about improper rotations. It's possible to have an S4 rotation even if you don't have a C4 or a sigma H symmetry. So this is actually a fairly useful trick. Similarly, you can apply our improper rotation to ethane, where this will have an S6 improper rotation, where I'll rotate the entire molecule 60 degrees, then reflect across the plane, and I'll get back right to where I started. Whether it's looking at the top or the bottom, again, 60-degree rotation, followed by reflection, I get back to where I started. So one of the things to watch out for is that this particular rotamer or configuration of ethane has S6 symmetry, but not every ethane rotamer will have the same symmetry. So this is one of the things you should definitely watch out for, is we're usually going to be talking about ground state molecules. There may be excited state molecules that have higher or lower symmetry. For example, we could imagine a gauche ethane configuration where these 2 hydrogens are in line, at which point we now have we no longer have an S6 symmetry, but we do have the sigma H. Now, one of the things to watch out for is that improper rotations are one of the hardest rotations to kind of get the hang of. So this is one that you may actually have to pull out a model kit, or feel free to go grab your WebMOA license, build the molecule, move it around, play with it. Honestly, physically playing with the objects is one of the better ways to spot harder to observe symmetry operations. So this brings us to our final symmetry operation, which is the easiest to spot, and that's the identity operation. So the identity operation is simply the idea of doing nothing. So every single molecule will possess the identity operation. And this is going to come in handy much later, as it ensures that all molecules possess at least one symmetry element. And it's also going to be very useful when we're going to be mathematically combining and describing symmetry operations. We want some way of saying that a series of symmetry operations did nothing, or that doing nothing is an actual action. So this is going to become mathematically useful, as well as helps make sure that when I group all of my symmetry operations together, there's somebody for everyone else. And that actually brings us to the topic that we'll be talking about next time. So far, we've talked about ways to identify individual symmetry operations, but as we noticed, especially with benzene, is there's plenty of molecules that possess more than one kind of symmetry operation. So what we're going to be doing next time is talking about symmetry groups and how we can combine, how we can make entire classes that help describe all of the possible symmetry operations that an individual molecule can have. And this will help condense a lot of our descriptions of molecular theory down to a much more concise form. Till then, take care and stay healthy.